Good evening, respected dignitaries, esteemed guests, practicing engineers, faculty members, and dear students. On behalf of the Indian Society of Structural Engineers, in association with Structural Engineering Department VJTI, I warmly welcome you all to today's expert talk on nuances of finite element method and appropriate applications using standard software. Before we proceed further, it is my honor to invite our esteemed dignitaries to kindly take their places on the dais. May I request our chief guest, Dr. V.N. Gupchup, former principal of VJTI, to kindly come up on the stage. I also invite our distinguished speaker, Professor D.N. Burgohain, former professor at IIT Bombay and founding director of IIT Guwahati, to take his seat on the dais. May I now request Professor K.K. Sangle, Dean Academics and former head of the Structural Engineering Department, to kindly join us on the stage. I warmly invite Professor Abhay Bambole, Dean Infrastructure and Maintenance, to the dais. I would also request Professor Tarun Khan, the Professor Emeritus IIT Bombay, to kindly join us at the stage. I now request Engineer Hemant Wadalkar, President of IISc, to kindly come up and take his seat. May I also invite Engineer Rangana Satum, Honorary Secretary of IISc, to the dais. And finally, I request Engineer Shekhar Ghate, conveners of today's program, to kindly join us on the stage. Ladies and gentlemen, a big round of applause as we welcome all our dignitaries to the stage. May I request all dignitaries to come forward and proceed with the lighting of the lamp. I would like to remind you all that this program is also being aired live on the official VJTI YouTube channel, so those who wish to revisit the insights later may do it online. To formally begin, may I now invite Professor K.K. Sangle, Dean Academics VJTI and former head of the Structural Engineering Department, to deliver the welcome address.
Good evening to everyone. It gives me immense pleasure to extend a warm welcome to all present in auditorium and online on behalf of the Structural Engineering Department and VJTI Mumbai. Today we are gathered for a very special occasion for an expert lecture on nuances of finite element method and appropriate application using standard softwares, which promises to be both enlightening and inspiring to all of us. At the outset, I wish to extend heartfelt welcome to our esteemed speaker, Professor D.N. Buragoin, a distinguished professional in the field of finite element analysis. Sir, we are truly honored by your gracious presence in VJTI today. Your vast knowledge and invaluable experience will surely enrich understanding and broaden the perspective of academicians and professionals. I also take this opportunity to welcome our respected ex-principal of VJTI and chairman of today's event, Professor V.N. Gupchu. I also welcome Professor Tarun Kant, Professor Y.M. Desai, Professor M.G. Gadgil, Mr. Shekhar Gathe, Mr. Hemant Vadalkar, Mr. Rangnath Satam, Mr. Jain Kulkarni, Mr. Shantilal Jain, Mr. Dr. Kelkar, and Mr. Professor E.N. Bambole, Professor V.B. Deshmukh. Professor V.B. Deshmukh is our present head of department. He has took over the charge on 1st September 2025. Professor S.S. Pendari and all distinguished professionals, faculty colleagues, and most importantly our students whose keen interest in learning makes such academic and professional gatherings meaningful. The aim of today's lecture is not only to enhance our knowledge, but also to bridge the gap between theory and practice, inspiring young minds to think critically, innovate, and contribute meaningfully to the society. Let me brief on Structural Engineering Department. This department is established in 1962 and since then providing academic, research, administrative, and consultancy services to the student, institute, industry, society, state, and nation. In past, this department is led by Professor V.N. Gupchu, Professor Sundaram, Professor M.G. Gadgil, and Professor E.N. Bambole. All these are the stalwart in the structural engineering field and already set very high benchmark for academic, research, administration, and consultancy services. At present, department having 11 faculty members with PhD qualification, most of them having more than 25 years of experience, expertise and competency almost every field of structural and geotechnical engineering. Recently, department has started M.Tech Structural Engineering program for working professionals with 15 intake, and this is the most popular PG program in the institute. Though the fee is 3 lakh rupees, but all seats are filled in last year as well as this year. Presently, 20 research scholars, that is the PhD students, are doing their PhD in the department. Last year, M.Tech Structural Engineering programs received the accreditation from National Board of Accreditation, and it is one of the PG program in the institute who received national accreditation from the National Board of Accreditation. Department has identified the thrust area of structural health monitoring and performance-based design for research and consultancy, and in process of establishing the Center of Excellence in these areas. Once again, I extend warm welcome to our guest speakers and all of you who have joined us today. Let us look forward to engaging an insightful session. Thank you very much.
Thank you, Professor Sangle, for those warm words of welcome and key insights in the department. We now invite Engineer Hemant Vadalkar, President of IISc, to briefly introduce the society and its vision for advancing structural engineering in India.
Chief guest of today's function, Dr. V.N. Gupta sir. Today's main guest speaker, Dr. Buragoin sir. Former structural engineering head, Professor Sangle. Dr. Bambule, Shekhar Ghate, Senior Consultant Dr. Kelkar, and Senior Structural Engineers and Civil Engineers, my ISSC colleagues, Mr. Nangaonkar, and students. It gives me immense pleasure to welcome you on behalf of ISSC and VJTI for this very interesting lecture on finite elements. This is a rare occasion that such kind of programs are, I think, planned, because we have different topics like building constructions, analysis and design and so on. But specifically on finite element, I think I am seeing the first this type of program. So I think we all will immensely be knowledgeable after this lecture. So this is the first kind of lecture I thought on finite element jointly organized by ISSC. Few words about ISSC. ISSC has been formed in 1997, and then under the guidance of late Mr. R.L. Nene, and there were 10 advisory trustees. Now we are 3,500 plus members in ISSC. All are civil engineers, mostly started for structural engineers, but slowly now we accommodate all civil engineers now in the field. And I appeal to those who are not yet our members, definitely you please become our member and support the activities of ISSC. Generally we arrange different type of workshops, seminars, lectures for civil engineers for updating the knowledge from time to time. We try to arrange sometimes the site visits also for students. And we are proud to say that now we are almost 12 student chapters in various engineering colleges nowadays, because we need better interaction between the professionals and the students. So that is what I think most important part. Similarly, we have also local centers in different parts of our country, like we have in Pune, Solapur, Aurangabad, Kolhapur, even outside Maharashtra also, we have set up some chapters. In Indore also we are one chapter now. And in, I think, Surat and Ahmedabad also, Shantilal Jain is also making some arrangement for making another centers over there. So basically, we want to coordinate with all our professional brothers, engineers, and to disseminate the knowledge that is what is available. Basically, it is a platform, I call it, ISS is a platform for knowledge sharing. That's what in one single line, if I have to say, we have to just whatever knowledge we have, we share with our fraternity to make our structures better. That is the only aim. That is the only objective of ISSC. So again, I welcome all for this very interesting lecture. We are very much eager to listen to Dr. Buragovind sir on the finite elements and what mistakes we are making in using the standard software. That I think is the most important part. Because nowadays, most of the design firms also, I see a lot of young engineers, they are coming in, they are very fast in doing the analysis. They keep on pressing the buttons and then come out with thousands of pages of output. But if you can't interpret the output correctly, then there is a disaster. So I think there is a word of caution again. I have to tell always my young students that, okay, be careful. Hand calculation is no substitute for any kind of software. That's what I learned from so many years and from my teachers all the way. Thank you very much.
Thank you, sir. We shall now proceed with the felicitation of our esteemed dignitaries. First, may I invite our chief guest, Dr. V.N. Gupchuk, to come forward, and I request Professor Bambule to kindly felicitate and do the honors. Next, I invite our distinguished speaker, Professor D.N. Buragovind, to kindly come forward, and I request Professor Sangle on behalf of VJTI to facilitate him. May I now invite Professor Tarun Kant for his felicitation, and I request Professor Bambole to kindly felicitate.
Incidentally, Bamboli is PhD student.
I was told of Professor Desai, but everybody still thinks that I'm Professor Tarun because I learned a lot from him.
I request Engineer Shekhar Gate on behalf of ISSE to felicitate our chief guest, Dr. V.N. Gupchu. They asked him to. That's fine. Then it was requested by ISSE that on behalf. I would again request Engineer Shekhar Gate on behalf of ISSE to do the honors and felicitate Professor D.N. Buragohen. The uncle can. I would request Madam Priyanka Bhivagare to kindly come up and join up on the stage to felicitate Professor Buragohen.
Mrs. Burak,
Yeah, that's
Madam Burak.
Madam. Madam, please.
No, you can finish this now. Come here. Yeah. Hello.
We now felicitate Engineer Hemant Vadalkar, President of ISE, and we request Professor Sangle to kindly do the honors. May I now invite Engineer Rangana Satam, Honorable Secretary of ISSC, for his felicitation. I request Professor Bambole to kindly felicitate. I request Professor Sangle to kindly honor Engineer Shekhar Ghate, convener of his event. Sir, can you please come forward for your felicitation? Finally, I request Dr. Kelkar to kindly join us up, and I request Engineer Hemant Vadalkar to kindly felicitate him.
He is one of the senior most in the gathering and senior to Professor Buragoin. Yes. When Buragoin was doing his PhD, he was already in the IIT as a faculty.
Ladies and gentlemen, the highlight of today's evening is our distinguished professor, Dr. D.N. Buragoin. Professor Buragoin is the founding director of IIT Guwahati and a former professor of IIT Bombay. His journey with the finite element method spans over 6 decades. He is a true bridge between theory and practice, guiding engineers in using software tools wisely, whether in meshing, element choice, or avoiding numerical instability. His contributions continue to inspire generations of engineers across the country. To introduce him formally, I invite our convener of the session, Engineer Shekhar Ghate, to come forward and introduce him.
It is really humbling experience for me to stand here and in front of 3 of my professors. Let me start with one very interesting incident or a story. In the year 58 or something, 59, one skinny young boy who has never traveled outside Assam, he stood first in their inter-science exam and he was directly selected. He has not appeared for JEE, not knowing much about IITs. IIT Bombay, that was the second batch. And he traveled by train first time outside Assam to Calcutta to Mumbai. And it was raining heavily. You know Mumbai rains. So he got down at Kalyan and then he traveled to Vikhroli station. Most of us, now Kanjur is the nearer station, but Vikhroli, that time Kanjur was not there. And he came outside. And then there was one gentleman standing with a felt hat and a shorts and with the jeep. So he called him, come, are you going to IIT? He said, yes. So, okay, join the jeep. So this young guy joined the jeep and he was dropped at Hostel 1. In the evening when there was a formal sort of a get-together, he realized that he is the director of the institute. He was a Brigadier S.K. Bose, and that is how he was introduced to IIT, and that is how the journey started in IIT. And then, let me not repeat basic this thing. He did his graduation in 63, BTech, MTech in 65, 69, PhD. Then he went to Swansea. He worked with Dr. Jinkevis. I will not call him father of finite element, but he's one of the pioneer. And then he returned to India. He joined IIT as a faculty, continued, guided. So, I can see so many of his students around. I can see here, sitting here. And some of them came only to see Buragoin. Then he continued in IIT Bombay, did lot of research work. I mean, I will not again take the names of this thing, but some of the very fascinating work. I think couple of work with Dr. Gupchup also for AERB, that dome failure and other thing. He might be showing some of the very interesting examples. Then he was selected to start the IIT Guwahati. Till then, there were 5 IITs and for almost 40-50 years. Then after a long gap, a new IIT started, and he was given the task. He was not interested in an administrative job. So everybody, all of us, how come he has gone to IIT as a director? Because here in IIT Bombay, he was hating the typical HOD and administrative activities. Then he went and he literally walked in water, and it was all slushy, muddy. And I had seen his office in Guwahati. He was operating from Institute of Engineers. There was no building, office building for him. And then he saw the IIT coming up in front of him. So it was a really fulfilling and like a satisfying experience for him, must be. And the understanding of FEM is what I have seen when we are working. I see a lot of junior people following it as blindly. There are so many instances where we use FEM without much knowledge. And our time when we started, Dr. Kelkar was one leading practicing engineer. He had that triangular element. Then he started, then isoparameric element, lots of element. And, anyway, let me not go into the detail. It is not correct. So we learnt a lot, and nowadays we have also forgotten. Now somebody asks me, what is the Gauss point? How it is transformed to the nodal? It is difficult for me to answer. So that is where, I thought, it will be, he happened to be in Mumbai. So I took this opportunity, and my friends, VJTI, Sangale and ISSC, Hemant and Shanti, they were all supportive, and that's how we are coming here. Again, I personally feel indebted to Buragoin, and I'll tell you, when we started, it was we used to use cards. I mean, younger guys, you have not seen a card. So we used to punch the card and go to TIFR from IIT. And it was and if there is a small little error, you have to, the whole program is lost. Then again you have to punch in, and it used to be, and then because of Buragan was my guide, I could work on the terminal. That time it was a great thing, we could work on the terminal. And he had a lot of sponsored projects, so I could afford to work on the terminal because it used to cost a lot. As a normal IIT fees, it was not possible. But amount of, and the way, he is the one professor I have seen, he used to walk in the class without a single piece of paper. And some of the people, Sabnis, they can vouch how uninterrupted, without a stop, without any, like fumbling, etc. And imagine, this is the FEM is highly mathematical. So, it was used to really elaborate. So it was a really pleasure learning FEM from him. And so I thought, let us share it with the general fraternity. And I really, I'm really thankful that I am in a position to welcome him and introduce him. Professor Buragan, please, now you can take the seat, so to say. I can't, speaker hai? No, we'll go down. No, you need to this or collar mic, yeah. Yeah. And it is all yours, and you, everybody can pass on the experience. What was the experience? It will be unique experience, I can guarantee.
Hello? Yeah, that line, but this is going to come in the way. No. Yeah. This way I put off because I have to. I should see it, no? Yeah. Okay. Can put to left. Okay. Right. Good evening, everybody. I feel very happy to be here today, this evening, to see so many of my old students whom I have not met for a very, very long time. And Shekhar Ghate was one of those students who had always access to me, and I think I have talked to him almost every year over the phone, and whenever I used to be in Bombay, because most of the time nowadays I'm in Guwahati. As usual, he always, Shekhar always talks a bit more about me, which I don't think I deserve. And among all my students, I think he is the only one who was never afraid of me. And he used to express his views openly, whether it is contradictory or whatever it is. And in the process, I always learned from him in the sense that he was always very practical. Practical side of things he always used to highlight. And of course, I am from the academic background more. I did not have much experience in the practice. So it was always better from that point of view. That way you can always learn from your students because there is always something new that come up whenever they face problems and I face problems. And you have to come up with a solution to the problems if it has not already existed. And if you cannot do it immediately, at least you can attempt to do it. Anyway, I think 2 weeks back, he had been to our house in Thane. And he just proposed that I should give a talk on finite elements because, many people use finite elements blindly. It is so easy nowadays. Everything is so user-friendly. So you tend to forget, the implications sometimes and use blindly and then land up in some sort of trouble when you find that the results are not what you would expect normally. Because there is always sense in the practicing engineer, there is always a perception how it should behave. Unless he has that perception of physical significance, he understands he's always likely to commit some mistakes. So they can always make out when the things are correct or some things some extraordinary thing is happening, though results may all look very nice on paper. I told him I'm not prepared because I have not got any material with me. Because whatever I had, the materials I had left in Guwahati. I had not come here to give a lecture or demonstrate anything. So I did not know. He said, don't worry, you don't have to come prepared. You just come there and we'll discuss. Then he found out this title of the talk. Now when he gave the title, I said, I am not prepared to do this. He said, don't worry. I said, okay, I'll do it on my way, because the way I got introduced to finite elements, the way I learned things, remember in our days there were no ready-made commercial software. Each problem that we tackled had to be programmed by us from basics. Check the correctness of the program, remove all the bugs, and then only we can apply it to the actual practical problem. This was the training we used to have, and of course we had spent hours and hours in doing this. And he mentioned about cards. We have started, from the slide rules. Many of you might not have even seen a slide rule, but we had started a slide rule. Then a mechanical calculator where you could rotate the drum, this thing. The only problem with slide rule was, of course, it could do so many wonderful things, but it could not add and subtract. So that was the only problem. Then the mechanical, this thing, 5-figure log table, 7-figure log table for surveying. Then the not pocket calculator, the calculator came by enormous cost. In 1971-72, a Hewlett-Packard calculator used to cost about 150 pounds. You can imagine how costly it was. Till the Casio pocket calculator came up, which used to cost 500, 600 rupees. Then people forgot about all the trouble they had in calculations. And slide rule, for example, I was never good there, because I always, some either parallax error or whatever it is, the calculation should be slightly always wrong. It was never always correct. So I had a problem. And when I used to start with the calculators, pressing it, I never believed the calculator. So I always, if the multiplication is there, I'll do on the calculator, then I'll do by hand and check whether it's correct. That is how you were trained. So, training was always from the basics. And on top of that, we did not have so many facilities of computers or something. TIFR CDC 3600 started in somewhere in 1961-62. And I think it was open to public from 1963 onwards. And I had to do my MTech problem in 1964. And my guide, Professor Sitaramolu, who migrated to IIT Delhi, he told me, you have to go and do this. I said, I don't know programming. He said, come to my house in the evening for a cup of tea. I will tell you what to do. And I sat across the table with him, and he showed me that Fortran programming, how it is done. And I found out it was very easy, except the only thing you have to think logically. So immediately I took a liking to programming, and he said, any difficulty, you contact Mr. Chandrasekhar at TIFR, he will tell you what to do. So that is how it started. And fortunately for us, in those days, TIFR tried to encourage people to do computer work. So time was free, computer time was free. We could go there. And when the first time I did some consultation work which involved computer programming, I remember staying overnight there, because daily, in the first, you could get only one run. Given morning, 10 o'clock, you give a run with that deck of punch cards. And if you are very lucky, it will come by 7 o'clock, you'll get the results. After giving the cards, if the card reader skips some card, then you had it. The whole thing is gone. Your statements won't be there. Or after getting a printout, when you come back in the local train, then you see there's a mistake in that somewhere. They have to run back all the way. They have to punch that particular card and give it for run again. That was the position. And that is how our struggle was there. See, finite element came into existence somewhere in our life, somewhere about mid-60s, though it started much earlier. So before I take up how using finite elements, what experience I had, I'll just give a brief introduction. Very quickly, I'll go through it. And see, this is actually after GQuiz's paper. It started simultaneously, initially with the mathematical side, then came to the physical side. And this is the mathematical side, Curran, and then Prager. These were the pioneers from the mathematical side. Then from the physical side, Krennikov in MIT. He was the first to try to discretize the continuum into a lattice analogy. both for bending as well as for in-plane forces in the plate. So replace it by a grid, the framework, and you can analyze the frame because by that time you knew how to analyze a frame. Though it used to be a lot of labor because we have to solve equations. Interestingly, therefore, you would always find that the development in finite elements coincided with the development in progress in computer calculations. If the computer did not come into existence, then finite element would not have progressed as it had done or evolved as it has done over the years. So after Handicraft, now we come to the main people, structural engineering people, who actually are pioneers in the finite element method. Professor Argyris at the Imperial College, in a series of papers, 1954-1956, the energy dealt with the energy techniques in structural analysis, and then Professor Clow of Berkeley, University of California, Berkeley. During his sabbatical during 1955-56, he worked with Boeing, and there he came up with this first discretization technique, the plane stress problem. And when he went back to Berkeley after finishing his sabbatical, he coined the name finite elements with the paper in 1960 and did a lot of work with his student Wilson, the creator of the EOETAPS or SAP4 programs. Wilson, he was a very good programmer. And all his initial work, he used to give to Wilson to program so that he could run and publish the results. So this is Clow. Then Clow met Professor Ginkiewicz. This is the O.C. Ginkiewicz, Olgierd Cecil Ginkiewicz. And in 1958, when Ginkiewicz was in Northwestern University. And when Clow told Ginkiewicz about this new method, then Ginkiewicz immediately caught on the idea and said that this is ideal for applying it to shell problems, because shell is always a problematic, closed form solution. Getting a closed form solution was not so easy. So discretized technique like this will help. So immediately caught on to the idea, and he went back in 1961 and joined the University of Wales in Swansea, Singleton Park, Swansea College. There he got a team, and incidentally, because Professor Ginkwiz's father was Polish, mother was English, and his childhood he spent in Poland. Then 1939 he shifted to London, where he did his PhD under Southwell, who was known for his relaxation method of solving equations. And he started with finite difference. Ginkiewicz started his career, research career, with finite difference. And he was in the government, in the hydraulics side, the hydroelectric power department. And he used to solve a lot of problems, dams, using finite difference. There he continued with that finite difference technique when he was in Northwestern, then switched over to finite element only after meeting Clow, and then 1961 when went to Swansea again, he got a team of people like Hinton, Owen and all those things. And most importantly, he got hold of Bruce Irons, who was with the aircraft industry. And Bruce Irons, in his own way, he was a genius. And when I went to Swansea, I met both of them. And I was there only for 1.5 years. And half the time was with Professor Ginkiewicz, half the time with Bruce Irons. And my introduction to finite elements was when I was doing my PhD. And there was a conference, international conference on matrix methods in structural mechanics in 1965 at Wright-Patterson Air Force Base there in Ohio. And then it's a very big volume. And there are all sorts of matrix methods are discussed, and finite element formed quite a lot of a part of it, of that proceedings. And somehow 1966, 67, I could get hold of that proceedings. And it was quite fascinating. And by that time, Jinkiewicz has published his first book on finite element together with Y.K. Chiang, and the next volume came up on his own in 1967. So I tried to do it, finite element, but then of course we did not have a formal course, learn on your own, so it was all trial and error. And my first finite element solution problem was with Dr. Kelkar. It was, I think, the Bhatsa Dam was raised in height. If I remember correctly, it's the Bhatsa Dam, yes. And it has to be analyzed for the stresses. And I was with Dr. Kelkar, and that was my first experience. And somehow, I think that gave confidence that results seemed to be okay, because that is all you can say, that it seemed to be okay after testing with something. And as usual, most people, when they learn finite elements, the mistake they do in the element discretization modeling. And when I used to, in my class of finite elements, the first thing I used to say that, you can use the element just like that, but you have to know the pattern of how the strains or the deflections or the stresses will vary. When you first test your finite element, any student will take a cantilever beam because you know the deflection value and divide it into elements, one triangular, and which will never give you this thing. I will tell you one incident, what happened. I was with, that was after my retirement, 2009, 2010, a German company. There was one apprentice there who was doing his master's, a German fellow. And we are to benchmark one program that we are going to use. So my people there told me, you take care of this fellow and get it benchmarked. So I said, there are so many benchmark problems. You please do this and analyze this cantilever first. So he did it. First 2 elements, no results. 3 elements, no results. 10 elements, no results. 100 elements, no results. 1,000 elements, no results. And 10,000 elements, no results. Because there was an automatic mass generation program, so you used to put that automatic mass generation program and get the number of elements went on increasing, but he forgot to increase the number of elements along the depth. It's only along the length. So you never get, constant strain triangle only give a constant stress, constant strain through the depth of the beam. How can you get a result? So that is the mistake. Most of the people, when they try out, they make it, and though their program and everything is correct, they don't get the results and they get frustrated and leave it. So this is how it happens. Then one thing lucky for me was there, that there were no facilities like, a research scholar's room or something in IIT Bombay that time when I was doing my PhD. So I had to sit at one table behind the structural classroom where lecture used to be there. There used to be a wooden partition. The 3 feet wide partitions you get, a lot of those partitions used to be there. I used to sit behind them. And all I used to do was do programming. And after some time, by 1966, I came to be known. Some people thought I am in the computer science department. Okay? And everybody used to come to me with their problem and do the program. MTech, PhD, other departments, any problem. I learned one thing, that everywhere, whichever department, whichever field, once you get the, whatever finite difference or whatever it is, once you get the differential equations, it is all the same. It doesn't matter which field you are working on. So you could always program it. And after some time, what happened is that even in the interview of selection for computer programmers in the computer science department, I used to be called as a member of the selection committee. That was quite, quite laughable, actually. So anyway, that is how it evolved. When I was doing that problem with Dr. Kelkar, I think I was just about finishing my PhD. And I did not use finite element in my PhD. It was finite difference, variational based. So that taught me quite a lot about the finite element. But I knew the difficulties that time. The research was going on about plate bending elements and the compatibility of elements. The other thing which was engaged most of the researchers at that time was the solution techniques for large order matrices. That time, whatever the mainframe computer could do, that is not even 1,000th time of what a present laptop can do. Not maybe 1 million time, maybe. It's so bad. Because CDC 3600 only had a capacity, memory capacity of 30,000 words, means 8 times one word, 8 bytes. So that was the memory, and you have to do everything. Even when DEC 10 came, still the capacity was less. And when the desktop came, 80, 86, and 89, like all that, same problem was there. Memory could increase. So half the time of ours was devoted to developing solution techniques. And also idealize the problem in such a way that you don't land up with a huge number of equations which you cannot tackle. So that is how it started. Now, when I went to Swansea in 1973, I, of course, met Professor Jinquist first, then Bruce Irons, and they were exactly opposite personalities. Bruce Irons was very polite, difficult to make out what he's thinking and what will tell you. And the most troublesome or most difficult part with him was that he thinks you know as much as he knows. That is the most difficult part. So he will know, you know this and then this like this. And that is how I will live. Then he will say, I am not understanding. Then he will not explain. He will just leave his paper there, scribble on a paper, or his published paper, something, leave it on your table and go. Now you have to make out on your own what to do. But one thing I was dead bent on learning there was the frontal solution technique for large order matrices. But she was kind enough to give me this software, coding. And I spent quite a lot of time going through every line of it because I wanted to adapt it for my use and be able to modify it. What is most important, be able to modify it to suit my requirement, right? So I spent most of the time with him. And then when I went to Professor Jinquist, he was telling me, these difficulties about conforming elements and compatibility. I said, yes. How to solve it? He said, you can try out several methods. There are techniques like penalty function, technique like least square technique, and you can even take nodes outside the element and get your elements. So I did that. Conforming elements, 2 triangles you take, those who know finite elements, and the problem was that the bending, the slope was never compatible between 2 triangular bending elements, between 2 nodes. You can write an equation, the difference, given the difference, square it and integrate over the line and multiply it by a very high constant called the penalty function, penalty parameter, penalty constant. Now, depending on the magnitude of that, you will get that compatibility. That's the enforced constraint that you get on that. I programmed it and gave him. Then I said that this is very unstable in the sense that I am never sure whether it will be compatible because how much bigger the number should be. He said, you try a range. Then finally I found out that if it is about 10,000 times, between 1,000 and 10,000 times, more than the modulus of elasticity value, you get that confirmation in this thing. But then I said that this is a problematic thing. Every time we'll have to program it separately. And he said, no, but that is no other way. Otherwise, you have to go for the patch test. That time, Irons devised that patch test for elements. Now, once the patch test came, patch test is a very simple thing. You take a patch of elements and apply a known deflection field. Apply on the boundaries of the node points of this thing. You determine, so it should bend like this. This is formula. Suppose you want the moment to be constant over the entire field. So if it is a quadratic equation of deflection, you differentiate twice, you get the curvature constant. So you get the moment constant there. Okay? So you use that, and according to your formulation, according to formula, apply those deflections at the boundary nodes and give it for run. And if your element gives the correct moment is constant, then it passed as the patch test. That's the simplest value. Then later on, they went on to prove that the patch test, if it passes the patch test in any element, that element is safe to use. You don't have to worry about compatibility or conforming this thing. So all the modern softwares that the commercial softwares that they are having elements, either triangular elements or quadratic elements, which may not be conforming, and it may not even be exactly satisfying the boundary. For example, if you shell, doubly curved shell surface, you are trying to divide into elements, quadrilateral elements, that quadrilateral will not never be able to map that surface. Impossible. Because the doubly curved element is non-developable surface. So quadrilateral element, if you 4 points on the surface of the sphere, if you join by a, it will be only a flat thing, and they try to lift it at the middle of the quadrilateral. They try to lift it and to go to that surface, but the element works. So people have applied that quadrilateral element together with triangular elements to doubly curved surfaces also, and they've got results. And that's why nowadays nobody worries. Ghate was asking me once, why, I have always used isoparametric element, 8-noded quadrilateral, which can map curved surfaces, curved boundaries, things like that. Then I was telling him that day that it's much easier to use triangle, particularly nonlinear problems also. So people obviously will use triangles because any surface to dividing into triangles is very easy. At the most a quadrilateral, but triangle is always the easiest solution. Calculations are easy. Meshing is easy. Whereas isoparametric element, the meshing is a problem. Find out coordinates of the middle nodes and all those things, known as a curved boundary, is a problem. So from the user point of view, therefore a triangle is the easiest. And therefore all the modern software will have a triangle and quadrilateral and automatic mesh, this thing. So the meshing on the computer becomes very easy. That is one reason. Because I have used triangles, but though I have earlier, most of the time I have used quadrilaterals, isoparametric elements, and which prepares some data is much more, complicated, unless you have a regular surfaces, geometrically definable surface, you can, have a minor preprocessor to get the geometry, or similarly do the post-processing to get the stresses. Now, this with the other thing that I did with Professor Jinkwis is that trying out the least square technique. The least square technique, you can divide, you can put a number of nodes, dots, all the surface, okay, several dots. Put them joined by anything like a triangle, arbitrary triangular mesh. Now take any node and find out the surrounding node minimum 6 or even 10 and enforce a surface, quadratic surface or cubic surface with the least square technique in terms of all the deflections of the nodes of the surrounding nodes that we have chosen. And that node, you can form a element defining the areas, dividing the area line between the two nodes and joining this by lines. So it becomes an irregular type of element, but it is identified with a particular node. The advantage of this finite difference as well, and this approach is that when you get the forces, you get at the nodes directly, and there is no mismatch of forces coming at a node from different elements, which happens otherwise. So it's the finite difference and the variational finite difference. This becomes a part of variational finite difference. It's part of this, it's a node-centric, whereas the finite element is element-centric. It is always element is the important thing. Here the node is the important thing. So this is how on this thing. So unfortunately, Professor Irons left Swansea to go to University of Calgary during the summer of 1974. So, but whatever I wanted to get from him, I got actually the frontal program. I learned from him that time. And later on, Professor Jinkwis, anyway, I told Ghate that though he told me, why don't you join? I did not join because I had a bond with IIT Bombay. So I had to come back. So I will go ahead and quickly finish this. This is the contribution of actually Bruce Irons, the isoparametric element and numerical integration. It was his contribution. And also the patch test. Now this is a picture I wanted to show actually. All these things was because of I wanted to show this photograph. This was the meeting of the three giants in the finite element field, Argyris, Clow, and Jinkwis in 1999. And out of them, the oldest was one, of course, Argyris, Next was Clough and then Jinquist. And all of them are no more. But it's a very rare picture. And I had got another one showing Wilson with a Clough, but I have not got it in this thing. So, and most of this, what I got here is from Professor R.L. Professor Taylor of Berkeley. In his tribute to O.C. Jinquist, after his death, he wrote a small this thing, and beautifully summarizing all his contribution. And by the way, Professor Jinquist is the first UNESCO professor, recognized by UNESCO, is the first UNESCO professor in the world. So this is how. Now I will slowly come to how I started. As I said, I started with Dr. Kelkar, and though I knew, means I got the confidence that I could program a finite element program, run it. The actual experience came much later. This was, I was showing this egg, this is the Professor Irons, he was a very, peculiar way of presenting things to the audience. This was his thing. He said engineers don't produce eggs, only hens produce eggs. That is a smooth surface like an egg surface, engineers don't produce, only a hen can produce. So don't worry about if there are kinks and non-conformity. It will work, it has to pass on little patch this. That is his way of telling things. Okay, now I'll come to my problems, what I did. My first major problem, this is related to programs like stats on something. What is the analysis of the TV tower at Worli in 1970-71? That time, it was, I think, somebody wanted to bid for that contract and came to IIT. And this was the Professor Ramesh I was working and was given. The first thing that stuck, it's very tall, almost 300-meter tall. And then so many nodes. And analyze the frame. How can we, 6 nodes, so not possible. It has to be only space truss, only 3 degrees of freedom per node. Okay, tried it, singularity. It will not go through. It took somewhere 2 or 3 times to realize that what is happening, that all the members that meet at a node, a joint, are not at, some of them are meeting only in one single plane. So wherever they are, whatever the number of members, if all of them meet at a node in the same plane, there is no resistance, because there are hence no resistance perpendicular to the plane. So it is a mechanism, and you will not get the results. So we started, we correct one place by joining a fictitious member, means a very thin member we put, almost 0 in this thing, and that value says some other passage is there. So then, okay, let us find out now. Find out all the joints, and each joint, how many members are there. Then go to the joint and find out if it is a joint in a plane of members. So identify all these joints in the plane. So once you do that, perpendicular to that, you can put a small spring, or you can even join that joint to some other joint at an angle to remove that singularity. That is the first lesson learned there, to tackle the frame members. So never attempt, unless you are equipped to the frame analysis, to do the frame analysis properly, with this proviso, don't attempt to use a truss. It is okay, truss is in the plane, in one plane it is okay, but not in space. Okay? Incidentally, after a lot of years, after the 80s, 90s, STAD came up with this. And when I was using STAD, later on, when I was in Pune, I was fascinated by the thing that they identified that each member joining another member, you could release the moments on any plane. And the most beautiful thing was that you can orient the member very easily, so user-friendly. But one thing about STAD Pro, there's one bug, I think it still remains in STAD. I was using the version 8, 8i or something. I don't know whether that version is there or something, but that was in 2012. That version was there, 8. Now, generally people will not come across this bug, but unluckily, what happened? I was in Guwahati and 2 years, away from Pune, but I was still under retainership at Pune. So, my junior engineer was analyzing one a reformer box, frame, steel frame, reformer frame for power plant structure. Then he rang me one day, said that I am not getting results. The equilibrium check by stat is not being satisfied. Equilibrium check is that after the end, all the reactions you get, and the external load is there, and it is very easy to, three-dimensional equilibrium check, 6 degrees of freedoms, 6 equilibrium equations has to be checked, satisfied. He says, I am getting the member forces correctly. He thinks, I think I am getting the member forces correctly, but the equilibrium check is not there. That means reactions are wrong somewhere. I said, you send me the data file. So I saw the data file and saw what he's doing. In that frame, it so happens that one of the supports of the frame is, offset to the actual support. Means a joint, there's just some rigid blocks and like thing that is supported. Though the node where all the members are coming at the end, that is not directly supported, but is supported eccentrically. So what we do generally, it is called a rigid body connection. The member is a rigid member. So rigid offset, in this that it is called rigid master-slave connection. So that particular thing, I converted data to my program and ran. I said the member forces were correct. At one particular node, the reaction was wrong. And that is the node support point, which is eccentrically supported. So I forgot about that frame. Then I took a small frame consisting of about 6 or 7 members and only 4 node support points so that I can quickly run and data preparation easy. And I checked. Now, STAT had another, this thing for accepting connection is a offset. The member is offset, end of the member is offset to the actual node. So same problem, I give instead of a rigid master slave, I gave offset. And immediately the directions were correct. Support points were correct. Now I realized what happened. See, whenever a programmer does a program, he tries to visualize all sorts of situations that can happen in practice. It is quite possible that this particular thing was not realized or not visualized by the programmer who did this part of STAT. Because the member forces were correct. And what must have happened is that, see, when you get the reaction directly, that point comes. Here the reaction was at some other point, not at the end of the members. All the members are coming to joint. So he did up to that and forgot to transfer that force from there to the actual support point. That part was not added. I did not point it out because I thought nobody will do it anyway, but I am telling you now that you have to be careful about this. So you cannot take everything for granted, even in a very good commercial program. Excellent program, but this problem, as far as steel frames are concerned, but this problem is there. So you have to be always cross-check anything you are deviating for the normal or standard procedure, you have to cross-check with another simple problem, not that huge problem which you are trying to solve, but a small problem. You take a small sample problem and try to check it, whether this works or not. Then only you can go ahead. So this second thing was in my, somehow in 1975, BRC had asked me to write 3 softwares. One is for plane problems, that plane stress, plane strain, axisymmetric problems. One is for 3-dimensional problems. One is for semi-analytical problems. That means one direction you can use Fourier series for this. So that was a good exercise. And I tried out all my, whatever I knew, combinations, things like that. And the BRC reactor engineering division, at that time Dr. Kakotkar was the head of reactor engineering division. And his engineers, all of them I think mechanical engineers, all were. And they were merciless in, in benchmarking, checking. They will find out each and every point over the period of 1 year. They ran those programs like anything and tried all sorts of problems. And once they cleared it, I was happy that my programs are correct, because they will not leave it. No mistakes were possible there. Then I got a problem. This is a more building problem in this thing. Is a telephone exchange building at Pune. In the floors were each floor, I think, I don't know how many, 3 stories or 5 stories, 7 meter high, double height. Because at that time, huge those telephone exchanges, all those boxes used to be there, not digital. So, and there all types of shear walls were there. There were no straight single shear wall, at least channeled, angled, T and different legs, length, a bit sort of things were there. And when the problem was given, I said, I will do it. I did not realize what I was committing. And then first thing is the space frame. It is no longer a task. 6 degrees of freedom. I cannot run in TIFR computer. I don't have the money to run it. So I have to reduce the degrees of freedom. The first thought. And my students, in those days, 77, 78, after 77, we remember the technique I used to teach there, how to reduce the degrees of freedom, 2F plus 2N or 3F plus 3N, N is the number of nodes and F is the number of floors. So each floor, you have only 3 degrees of freedom in the horizontal plane. Each floor-wise. Each node has the other degrees of freedom, which are perpendicular to the plane of the slab, vertical deflection, and 2 rotations about 2 horizontal axes. So thereby, you reduce the number of degrees of freedom, and your bandwidth reduces. That was my approach. And that I got when I was, actually I was cheating on my invigilation duty, sitting on the chair there with the table, and trying to find out how to solve it and hit upon that idea. And that is the diaphragm constraint, what you call the diaphragm constraint, rigid thing, you do it. Now, as he's pointed out, that does not solve the problem. I have solved the solution problem, but idealization problem is not solved. Because that type of shear wall, you cannot take as a single column. Because first thing, if you take a single column, then what happens to the rotation, twist? That is the twist of the building, or even rotation about the vertical axis. You have to find out the shear center. All those calculations are necessary. Who will go through all that problems? Now, what to do? I think that question is still there with his mind, what to do. I will come to that later on, what to do, because I have got a solution there. I tried out that solution that come at the end. Now I will go to after that, what happened. I had a problem of Pelton runner. This was from hell, this problem. This was for a hydroelectric project at Malaysia. Sungai Piah is the name of the place, hydroelectric project. They had to have 2 Pelton runners, one upper skim, lower skim. And unfortunately for them, the consultant who were, approving this was a Canadian. He said that he requires full stress analysis of the Pelton wheel, the buckets, for 2 or 3 conditions. One is of jet forces. As the vanes are moving, jet will strike at different angles, different thing. That is one of that. One is that suddenly it gets locked, jet forces are there, so force will be much more. The third is the freewheeling. You lose control and it starts spinning wildly, very high speed. So that is a purely centrifugal force. Now, those days, it was sometimes in 1984, 85, when I got the problem. Those days, this solid modeling and all those software are not there. The surfaces were not even digitized. So all that gave me cross-section, divide the bucket into several sections in both directions, and give me the diagram of the short section. I have to measure from the diagrams the coordinates and find out x, y, z coordinates. So if headcare is wondering about that partnership is how much data, how much provided, this was much more than that. You see, this is 3D. It's much difficult, and it was not a regular surface. So I had to divide into 3D element, three-dimensional elements. There was no other way. This is how it was giving. That one, both sides were giving. Both sides, horizontally, vertically, bucket. It's a half bucket. So I had chose three-dimensional elements, all isoparametric elements of various kinds to fit into all, each and everything, this thing. And I had to find out the coordinates of each of the nodes. Of course, they are not all curved. Why should I use a curved element if there is boundary is not curved? But in general, this is how it is. This is, if you take one plane, on the splitter plane, if you project, it is how it looks like. Otherwise, it is a 3D element doing this, and you have to find out all these things like this. Now, how to do it? There are so many, as you saw in the initial first plate. There are two, and there are so many buckets. Now, but they are all repetitive. So what to do? Then you go to the condition of cyclic symmetry. You know, the buckets are repeating cyclically. It is exactly the same bucket. You just rotate by some angle, it becomes next bucket. Again, rotated by some other angle, it becomes next. So in that polar coordinate, in that diagonal, your geometry is exactly the same, all the buckets. So what you can do, you can take only the connecting points, and if it is, for example, the centrifugal force, each bucket will behave exactly the same way. So the boundaries of two buckets, this I am showing cyclic symmetry, and the boundaries of each bucket, the line joining the boundary, displacements will be, there are suppose two lines, one bucket here, another bucket, one line here, this bucket and this another line. Displacement, the polar coordinates in this line and this line should be identical. A displacement constraint you can put as boundary condition. You can get this solution easily. And thereby you reduce the whole problem of so many buckets, reduce a single bucket problem, just by putting the proper boundary condition. Now, how to do about the other Z forces? Now, once I get, again, this one bucket stiffness matrix, in terms of the nodes, nodal displacements, again in the same coordinates, that becomes a substructure. I can get a stiffness matrix only in terms of the boundary nodes. So I can combine all these stiffness matrices to get the stiffness matrix of the whole structure, but not in terms of so many nodes. It is only the common boundary nodes. So your stiffness matrix size reduces, and you can solve it. So that is how I did it. Now, the problem is, I know many of the commercial software have this substructuring problem, some don't have. But you have to be able to use it, because it involves 3 steps in the analysis. First step, do the substructuring, that is, find the substructure stiffness matrix. Next step, combine them to get the whole analysis. When you do substructure, you have to not only define the substructure stiffness matrix, but also substructure load vector. It means effect of all the loads in terms of the boundary nodes, transfer to the boundary nodes, and combine. Now you have got the displacement. Then third stage, final stress calculation stage, you go back to the original substructure. Substitute the boundary conditions for that you boundary values, actual nodal values that you have got for displacement, substitute there, and resolve that, one with the loads in there, so you get the stresses in that particular bucket. So 3 stages, nobody wants to take this trouble. But I, that time, did not have any option. I had taken the problem, I had to solve it. However, how much time, effort. And the worst thing was that there was no plotter. See, the, what we call laser jet, not laser jet, dust jet, printer, which is there. Whatever you see on the screen, you can transfer. That time it was not there. I'm talking this thing. This came only in 90s. It's not there. So all I could afford was a pen plotter. You know, pen plotters could be either 3 pen or 5 pens of different colors, and the plotter thing is there. So all that it does, you ask the pen, one pen to drop. So it drops at that particular coordinate. Then ask it to move to the next coordinate. It moves along the pen moves on the paper. So you draw a line. Then lift it, then move to the next coordinate, go there, and drop the pen. So this is how the pen plotter works. And even if a circle you can draw also, because you have to divide this circle, the circumference, to, let us say, 50 segments, small. After all, it is only, it will produce the curve, perfect curve. That is how it was there. And what I did that time was write this program for the plotter. That time there was a, two types of these things were there. One is a plotter, pen, I don't know, remember the thing, but PPT was the, PPN or PPT was the extension name of the file. For that, another HGL, HG plotter was there. You could get it. Later on, when I became a bit familiar with AutoCAD, what I did, I used to write a program. After getting the results, I would write a program for plotting either on HG plotter, PP plotter, or AutoCAD DXF file. DXF file is a text file, so you learn how to, what is the contents of a DXF file, and you prepare a DXF file, then you run the AutoCAD program to give you the thing. But the problem is that the plotter, till the plotter became available, that type of continuous plotting, that was a problem. Okay. So this was an enormous effort, much more than that variance bridge you were talking about. It took a lot of effort and a lot of time, because there was no, thing is that there was no machine. IIT did not have a mainframe computer. TFR computers were costly. And desktop computers only, that was 8086 was available, which was very, very weak. So this is how the problem I attempted and solved and got enormous satisfaction. It was a difficult problem at that time, very difficult. I think the problem is difficult even now. It is not so easy to solve this problem, because it is 3D elements and that segmenting, so many things are there. Now I'll come to this bridge. Khetkar was the, this thing, the Varanasi bridge. This photograph was supplied by him, so I took advantage of recently, last time you came, you gave me that photograph, I am producing it. And the uniqueness, he knows better than I know, uniqueness of this bridge is that this whole thing monolithic, single integrated, right from the well foundation, well cap, on top of the pier is there. There is no, bearing, nothing, nowhere. It's a single thing. Then going up to the top of the pier, both the cantilevers going up. Again, no support there. It's a completely monolithic. Only thing is that, oh, I missed somewhere. Oh, I think it is, yeah, below, that one. So I think there are so many piers. I am showing pier 6, pier 7, pier 5. There's a purpose for this. So this was connected. And the two, the cantilever ends of the two consecutive piers were connected by hinges, two types of hinges. The vertical hinges, which will allow you to rotate, this thing in the waves, which will not allow horizontal displacement, differential displacement horizontally in the waves. That is the vertical plane. The hinge is the vertical plane. The top, this thing is in the horizontal plane, the wave hinge. So it will not allow vertical movement, but it will allow horizontal rotation later. So this was the condition of hinge. Now again, the dead load, of course, always is easy. Live load is a problem because the train of the loads will move, and sometimes part of it will be one cantilever, the other part will be in the other cantilever. The third thing is the sinking of one pier, the effect of the other two piers standing still. So any stresses will be produced. The fourth is the horizontal, the transverse wind and earthquake load. Again, this we have to all of them, the interaction between the three segments. So I only showed for three segments. Others are there, the effect will be minimal there. So only these two neighboring segments and this central segment, these are the main ones to get affected. So this is this thing. Now again, what to do? Substructuring. Get the substructure stiff matrix at the hinge in terms of the hinge displacement there and both sides and do this type of analysis. And here I chose, first I thought I will have to use, because as you can see, the cross-section changes, thickening is there, obviously, has to be there, the roots. And first I was thinking what I should use 3D, but then I thought that 3D is not necessary here because it is quite a huge thing, and you can, this is how the overlapping things will do. This is how the pier, the well cap, and the two cantilevers, then the top cap of the pier, and the diaphragms. That is how this thing was done. And then when you see this is how the wireframe, this thing. By the way, this was the fag end of the thing. I could get a DeskJet printer to print that out of that wireframe model. This is from AutoCAD, actually. I could, from my program, I could convert it to. And the other problem is, those days, when the DeskJet printer was not there, and the ready-made software, graphic software not there, is how to hide the, to make it more, readable, how to hide the hidden lines. Only the visible lines you plot. In the computer thing, in screen you can do. You can, grade from you decide your viewpoint, your eye coordinate, the distance you are thinking, and you can project all the points into a single plane there by, projecting, and then find out the distance of each element or each node from your eye. Then you find out, first plot the furthest one, then that element, then when something else is coming up, and you color that, the color behind is obliterated. So finally, when you go on that process, finally you get all the elements and lines which are in front of you, and hidden lines and elements are gone from the view. That is okay on the computer screen. But if I have plane plotter, how do you do it? Plane plotter, I cannot plot and then erase. See, I have to select also only the lines which are visible, not others. This was sometime in 80, this one what I was doing in 84, 85, 1984, that before. No, that was afterward. But before that, I prepared for this. I could do it, So I took, during this summer, I took leave, 15 days leave from the institute. I got desktop computer at home, just by my bedside. And 15 days continuously, I was sitting there, reading my solid geometry, revisiting my solid geometry days, transformation of coordinates, all those things, projecting of coordinates, and then how two lines cut. And at the end of 15 days, I could find out by the same process, the length of the line, where the line is cut by another line. So that only that segment of that part of the line only I will plot, not the other part of the line which is hidden by things. So all the intersection points I have to find out. So it's a completely new set of lines and coordinates I could get from this process program, and then I could put on the, the plane plotter. But it worked. I don't know, a computer science student or graphics who are expert in graphics could have done it much simpler way. For me, it was a challenge. So I had to do it. So I did it, completely devoting all 15 days to this single problem of finding lines, cut lines by surfaces from this thing, and going through my elementary, all the whatever we have learned, and what did this. But it was enjoyable. Because it's the one thing, I always enjoyed programming. And therefore, doesn't matter how long I am sitting on the computer and doing the programming, it does not tire me, even now. So I always used to do that. And so I could do that, and that was satisfaction itself. And this is finally the wheel loads. Wheel loads passing from one end to the other, and after all, the computer is doing the calculation. I am not doing the calculations. So once I do it, and I progress the loads by 1 meter at a time. Go on doing, and I keep a track of the stresses coming on the important points, and retain all those stresses which are the maximum this thing. So I don't have to find out, we do in a theory of structures, when the moving load is there, what is the maximum influence line, all those. Do not worry about that. Just physically, brute force, you make the wheel loads go 1 meter at a time and find out the stresses. And since I am not doing the calculation, it's okay. The machine is doing it. This is another, I did a lot of problems, solved a lot of problems for Gammon. That bridge was, when Dr. G.P. Saha, I think, was the chief engineer in HCC, did it there. G.P. Saha was earlier in Gammon. And the first time he came, I met him, was in 1976, actually. That was a sand blow condition in a wall foundation. Sand blow condition, those who are in bridge, this thing will know, when you sink the well. And then suddenly liquefaction of the sand is there. One side, the sand blows out, it becomes empty, so you don't get any support there. The other side, the sand is still there, pressing hard. And just because of pressure from this side and some side of this segment, there is no support from the lateral support from the sand. So tremendous force is created. And I've been told that the wells are split vertically because of this tremendous force after sinking, and if sand blow condition happens. So you have to check whether it will, if your staining is strong enough or thick enough to prevent this type of happening. This, when I first saw this problem, I thought, oh, I'll have to, he said, how will I take the forces? He said, it is self-equilibrating force. You are the vertical, it is coming, but horizontally, force is coming and one side is supported, other side is pressing, so it is a vertically balanced. So we have to artificially, we have to create a boundary and then get these forces working outside. First I thought it was a three-dimensional problem. The forces are not equal, this only part of it is this thing, other side is not there. So how to take the forces? Then after a few days I realized it's a 3D problem, okay, but solution need not be in 3D form. Because if you take a circular obstruction and horizontal, uniform horizontal force is coming from one side, that force can be easily expressed in terms of just P cos theta. Because it will be, that force will be always perpendicular to this curved surface. It will not be tangential. Tangential has no purpose there. So once you transform it to a radial force impacting on the surface, circular surface, that whole radial force is a cos theta, whole thing a cos theta. So I can use that, what we call that semi-analytical technique, or just single term of the cos theta. The forces will be also cos theta. Distribution of forces will be also on the cos theta type of thing. Both sides, this cos theta, this side. Only the angle of this thing will be different from the two sides. So if you do that semi-analytical technique, then it becomes very easy. Then I can divide the vertical staining into any number of elements I like, and the solution is very easy. And after getting that, I told Dr. Saha, oh, I will charge only this much. Because I did not tell him it is so easy. It was looking so easy after that thinking. He said, okay. Later on, after I did that Varanasi bridge, one day Dr. Saha told me, you don't know how to charge your fees. I said, why? You know that problem I gave you that time in 1976, Well Foundation, the minimum quotation was 6 lakhs. Then you charged only 15,000 rupees. I said, you should have told me. He said, why should I tell you? You charged, you thought that is how much. I said, see, I thought it was a very simple problem for me, so I charged. So you will never be able to business, he told me. This is not how you charge. So anyway, that is the first introduction to this. And later on, I came across several other problems. So Gammon, I will come into that later. But this was the last problem I did for Gammon. This was over the Tista. Anybody who has gone to Sikkim side, crossing the river Tista, they must have crossed over this bridge. This was in 1991, 91, 92, that type. Started in 90, I think. This is a 138-meter gorge of the river, and they did not want any support in between anywhere. No, so it was just an arch bridge, and it is visible from distance. It's a parabolic arch, and then over the arch, RCC arch, there is a columns are there for the road surface, where the road surface will be there. But first for that, you have to construct that arch. Now constructing that arch without any support from below over 138 meter was not possible. So the thinking was that okay, very lightweight steel frame of this type we'll construct from both sides and join at the center so that the gantry can move on this frame, getting concrete so that concreting can be done from both sides. And of course, after this, the reinforcing rods were also there. But the gantry will basically move over this for the concreting part. And of course, at the end, it is all solid, concreted thing is there. It's a rigid support, fixed support there. Here only the frame part is shown like that, but it's covered up like that. The idea was to, first, the concreting was to be done in 7-meter segments. The first end 7 meters from both sides you simultaneously concrete, so it is symmetrically loaded. And what happens? Because it's a very lightweight frame, it pushes up that center, it goes up. So next time you concrete the center part, so it comes down and flattens out like this. So this process goes on. So the fear was that in this process, maybe this shape will be lost. This was a problem for finding, retaining that shape will be there. That was the initial problem. Now that is okay thinking. When they gave me to analyze it, I said, how do I do it? This, if it's a steel frame, I can do it very easily. Now you are concreting this side, that side, there, somewhere here, and it is no longer a steel frame. It is a composite frame. And with an embedded frame, steel frame inside the RCC. How do I do it? Now, that was a problem, and I did not have any solution. So what do? I try to devise an element. This is a beam element. This is a beam element that is shown, and inside the beam element, there is a steel segment. Now, I must find out what is the contribution of this steel bar inside that RCC to the stiffness. The easiest way for me would have been, for example, here, I segment that to concrete RCC, concrete elements. I segment that same part, the steel elements, and at the nodes points of that concrete element, I put a rigid constraint, diaphragm constraint to the steel frames so that the shape of that thing, no deformity is there, because as consistent with your beam assumptions, the plane remains plane and rigid. It cannot deform. That rectangular face cannot deform. So I could have done that. But then what happens to the members between that and the other node? They are free to deflect. They take their own shape. Their strains need not be consistent with the strains in the concrete, surrounding concrete. So that will not do. I could do it, and I could say that, no, it will be okay. But anyway, that did not, I don't think it was, I did not think it was the right thing to do. So I had to devise an element of this type where it can take a steel member, and this took some time. I took about 2 months to devise this element, test it with a cantilever, and to get the results, acceptable results, then thinking separately, taking the steel frame and the concrete member, and then superimposing the stiffness and then running and putting it here, and I found there's a difference. So I did this. After doing this, what happened? I could do this. First, no concrete is there. Next, both sides 7 meters, concrete is there. Next time, 7 meters, 7-day-old concrete. This is top, fresh concrete. 14 days, after 7 days, first 7 meter, 14 days concrete, top it is 7 days concrete. So it will go on. You know, the different strength of concrete is there. So you have to take that. Of course, you can easily put in the computer and go on doing it. And finally, what I arrived at is that the shape, more or less, does not distort that much after all this doing. But then something has happened. During the initial stage itself, that whatever casting was done, concrete, that failed in the moment. That will fail. Enormous moment coming. I was breaking my head, and the Gabon also, whoever was working with me, breaking his head. Why should the arch? It's an arch. How can so much moment come? It took some time to realize that this is not an arch. It has not become an arch. Till the whole thing is concrete, then it will take load, then the moment will not come. At that time, it is just loaded at the center, something loaded at the center, and a very weak steel frame, lightweight steel frame, and it is not behaving like an arch. So the moment will come. So the solution is ultimately that at a quarter span, you put a trestle, some sort of support. So initial thing did not work. Whatever the idea was there, so the entire thing was in vain, except that the negative results also was in a conclusion that you cannot do it. You should not do it. You have to support it somewhere to prevent this type of thing, the casting. So that was thing. That it was a lesson. That was in 91, 92. This is the problem of 94, 93. The dome of a, cylindrical wall, and that at top of a dome is there, and the dome is pre-stressed, and the cylindrical wall is, of course, a ring beam is there, then the dome is there over the cylindrical building, and then the raft is there. And the pre-stressing was not the usual radial or this thing, it was rectangular, orthogonal pre-stressing, the way it is shown here. Now, during construction, with the pre-stressing of the cables, the dome collapsed. Not collapsed in that way. The lower part, below the cables, the part of the dome below the cables, that concrete fell off. Yes, literally it collapsed. Now, problem is, of course, the usual blame game was there. That the materials were not proper, that's why it failed. The construction people say, no, theoretically it is wrong. So all these things going on. So I was asked to investigate what caused the failure of this problem, of this surface. Now, this surface I showed here, it is a single surface. It is called I am calling the interface element. I divide the upper part, the dome, RCC dome, into two layers. The cables are running at the center, so two layers, upper layer, lower layer, but the nodes are the same between the common nodes between upper layer and lower layer. And these same common nodes, I don't use the same node numbers, I use different node numbers. And join these node numbers by interface element. This element has 0 thickness. And giving it a stiffness perpendicular and tangential stiffness, so that if the stiffness is high, it cannot slip. Vertically, it cannot punch into one another. Horizontally, it cannot slip. Now, if I can put the forces at that interface, cable forces, correctly, then I should be able to find out whether this interface, the stiffness, vertical stiffness, will show, stiffness means deflection. Now, two nodes are there. Maybe they are 0, geometrically they are at the same point, but theoretically they are different, and it's connected by a sort of a spring. So if these nodes try to come together, the spring will show a compressive force. If they try to show going up, that spring will show a tensile force. And if it is tensile force, it will tell me that it is trying to fall apart. How much tensile force? Now, there are two ways of doing it. This is there, same thing I said, node upper level, node lower level, node with the same coordinates, two surfaces. And I could have given spring values to all these joining to these two nodes. And that spring value will tell me the stiffness, the force coming, and then I can distribute that spring force over the surrounding area to get the stress. The other option is the surface itself is suppose the spring, Shekhar Khate was telling about Gauss point and all these things. You can hold surface is an interface connecting these two, and if the stiffness is there, the normal stiffness is there in that, and if trying to separate out, it will show me forces, tensile forces or compressive forces. If compressive forces are there, perfect. If tensile forces are there, then you have to find out the limit. If it is exceeding the limit of tensile force, similar tensile force, then it will, of course, separate out. So as usual, I think sometimes I try to complicate matters or whatever it is. I have to, chose the surface, the interface element. Actually, earlier to that, we had published some papers to interface element. We can soil structure interaction. Below the foundation, the soil is there, and the interface element, what the soil is, how it will behave. So same interface element, I adopted this. And another party also was given this task, and we discussed, and they chose to use springs, individual springs, and divide by the surrounding area. And somehow it turned out that both our results were within 5% difference was there. I will not know which is more accurate, but difference was only 5% was there. And it showed that it exceeded the permissible value of tensile stress in that direction, normal stress, and so it fell down. It separated out. That was something very helpful to learn that the things, I know not everything theoretical, sometimes it works in practical also. And you can solve practical problems by this. Now, this is, I'm showing this. This is a 3D element, which I used in this problem, that the dome problem. Because upper surface is there, lower surface, upper surface, the brick element, 16 node, it varies parabolically along the surface and linear, this thing. And bottom also, it's the same thing, so that I can divide into. And entire structure, I divided with this element, and including the I missed something. Including the ring beam, which I did a 3D element, 12 nodes, 4 corner nodes at 3 sections, 12 nodes. Now, what I'm going to tell you next is that if you have a 3D elements in the program, say for the 16 node element, earlier I showed that, this one, you can use it for plate bending without any problem. The entire trick lies in, behave it like a plate, and that is a very small input. You have the rigidity matrix where the E and diagonal terms, and then the ET cubed by 12 into 1 minus nu square like that, the nu times of that on the other side. All that you have to do corresponding to that 3 times the element stiffness matrix, where that sigma z, normal z comes in, you detach the diagonal elements, make 0. That means the normal stress is not connected with the other tangential stresses, no connection. As soon as you do that, you'll get, even for a thin plate, you'll get results, correct results. Absolutely no problem. Same thing happens to the beam problem. If you, the 3D beam element, the normal stress means longitudinal stress, and the other 2 stresses, if you put 0 values off diagonal, and only the normal direction you don't do anything, whatever, you will get correct results even for the beam. And this I had tested when developing the programs for BRC during 75, 77, during that period. you know, for a beam, for example, if you line linear beam, even if you do a 6-node element, the aspect ratio, that the thickness value, if it is 1, the length value can be as large as 400, you will get correct value of beam without any problem. No problem. That no singularity comes, nothing comes, no numerical instability anywhere. Same thing happens with plate. So I could use, because I had that previous experience that I could use it, I use this for the dome element. And even if you're the commercial software, if you have a 3D element like that, you can use this, provided there's a proviso there. See, I said normal stress, but unless the plate is flat, if it's a curve, direction of normal stress will be different. So you have to transform the stresses and strains into that normal plane and the tangential plane. Once you do that, you can put this. But that transformation is required. I could do it because I am doing my programming myself. In the commercial software, whether that is possible or not, I will not know. Okay? So these are the small things. Now I am justifying the word nuance used by Shekhar Ghate. These are small nuances in finite element technique that, what's the time by the way? Huh? Oh, as usual, you know, I am used to giving, I never used to take 1 hour lecture always. I always used to minimum, I will also take 2 hour lecture throughout. So same thing has happened. So anyway, I am concluding now. This is the element which, anyway, he is not there now, which I can use in the shear wall. Each component of the shear wall, the vertical direction, this element can be used because this is tested both for open cross section and closed cross section. In wall beams, open and closed cross section, to reduce the number of elements. The single element in the plate, single plate is enough. You can take, and of course on top and bottom, you can diaphragm, that constraint can be used. The next, this is Khedkar, right? It's a pump house problem. Now I don't go, because unfortunately I have not got the results files, I have not got. Somehow I dug up this from one of the drawings. I look at it in some pile of papers, so I just put this. The pump house, walls are there, all these things. The cutouts are there, and then the 5 vertical pumps are there, and they're checking for the natural frequency, of course, so that there is no question of any resonance happening like that. And this problem, initially I thought of using only 8-noded this thing, but then I thought effect of wall will be there. If I simply support it also will be wrong, fixed also will be wrong, then why not divide the walls also to elements? So in that process, the joint is a problem. So I use that 3D elements, the paralinear which I showed earlier. Throughout I use that 3D element and solve the problems. I think at least he was satisfied, I think. So the last I am showing is this last problem I am showing how, I think I started late. I did not start at 6:35, so it is okay. This is the cooling tower problem, Gammon. I had solved 3 cooling tower problems for Gammon. This was the last one and the most difficult one. The other cooling towers were given directly, only I had to use the wind load for finding this thing. This one was having that diagonal columns, basin trough, and the rough foundation, then solid structure interaction imposed on that. So I do this. Now, yeah, there is something at the bottom, you see. I cannot solve the whole structure. It is not possible. Because that time only I had the desktop computers, so it will not hold. That much memory is not there. I could at the best analyze only half the structure. And it shows the degrees of freedom that coming. The full tower 13,800. Quarter tower is only 3,500. I decided I will go for 3,500. On top of that, using that desktop computer, and it takes 10 hours. So run it, give it for a run about 9 o'clock at night, come back next morning, 8 o'clock, to check whether the AC was working all night or not. If it was not working, then the computer will get heated up and your thing will stop. So pray to God and run it. And luckily by that time, we had, I think, at least 2 desktop computers side by side in the same room. So what I did, physical parallel processing I did, not the programming parallel processing, the physical parallel processing. I divided into, I only considered a quarter of the structure, okay? Now, any quarter of the, this thing, if I put boundary conditions and the 2 symmetry planes, boundary conditions, I can put symmetry condition, symmetry condition, symmetry, anti-symmetry, anti-symmetry, symmetry, anti-symmetry, anti-symmetry, 4 conditions. If I use the whole structure, I have to analyze only once. If I use half the structure, I have to analyze twice. If I use the quarter structure, I have to analyze it 4 times to get any type of loading, stresses for any type of loading. So I chose the less because I could tackle it at least 10, let it take 10 hours at least to run in 10 hours. So give in both the computer, this thing, give symmetry, 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 anti-symmetry. Next time you come in, anti-symmetry, 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 symmetry. Twice I have to run. And then combine the results by again, results you have to combine. So this is how things were tackled, you know. And that is because I was doing the thing myself. I don't know how it is possible, but I think it is still possible because this will be much simpler in the commercial software because discretization meshing is easier there, and the results, correlation of results also is much easier. But that time, when it was not there, this was achieved through this. The last part, during my, what you call it, sojourn in Pune, rather, my venture into industrial in the field. I was working for civil engineering network systems of Germany, Bochum, Germany, head office there. And one of the partners there, 2 partners are there, one of the partners there, one Mr. Gerd Spies. And he had bought, during all this time, by 1980s, after developing those programs for BRC, I had decided I will solve all problems in desktop computers, and accordingly made by this thing. And this piece somehow knew about this. This program was of course transferred to Godrej and Boys. They had the electronic development division, which became Green, I don't know what was it called. One of our students were working there, software. They acquired it and gave it to him, sold it to him, rather like this. And once in 94, 95, when I was in Guwahati, this piece used to come every year and ring me up. What are you doing? I think you should leave IIT. You have spent enough time and join the industry. I said, no, I cannot leave IIT. I'll be there. 95, he called me and called me to his hotel here. Both of us went. Then he showed me, see, this program, this thing like that, I am showing you the big thing in Germany, some structure he's analyzing. What do you call sculpture. I said, oh, very good. All the 4 sides of the screen are all those small icons are there. You press one and then one thing comes, a mesh, something is there, all this there. I said, it's a very beautiful program. No, it's working. He said, it is your program. I said, I never had all this. No, I had employed one computer engineer, good in graphics, to develop all this, icons all around that, so that with the pre-processing and post-processing thing, you can do well. And I asked him, you should give it to me. He said, no, you had sold me yours. I am not going to give this because I spent money on developing this. I said, it's not fair. You have got the program from me and not giving me the thing. So anyway, this is, when I joined that firm, the first thing they showed me, see what was to happen, this German company, head office, they used to get the contracts for structural consultancy, that analysis design, and then construction also, supervising the construction also. This is a structure in Las Vegas, Lurevo Center for Brain Health. Now, when I first saw this, they showed me a model when I joined the office there. So you have to, this is the structure. I said, oh, I mean, are they preserving that World War II damaged structure still now? It looked to me like a brain, damaged, bombed structure, all deformed in all sorts. No, no, this is the one we have to analyze. I said, how come? No, this is for a brain health institute. And the architect thinks that distorted brain looks like this. That's why the shape of the roof is like this. We have to do this thing. I said, who will discretize this? He said, no. Luckily, he giving the digitized surface. We know all the coordinates, wherever you want. We analyze this. So this is how it started, my this thing, industrial career. What happens? Why it is not moving? Why is it moving up? So this is the discretization, finite element discretization. We used a program which is called, Australian software, Strand, or the Germans used to call it Strauss, but in the manual it was written Strand. Anyway, this is how it was discretized, and of course there were 20 engineers working on it. So it was okay. I had to check that discretization is correct. And we had to use orthotropic elements because there were a lot of rips were there. So initial thing we used to orthotropic elements. Then of course final discretization was there in this form, like this. But finally when that, okay. So this is what happened. This is, the architect is the world famous architect, Frank Gehry, from Los Angeles. And his structures has a peculiar form. They are always distorted. They are never straight. Anywhere you go, if you saw a distorted type of structure, you know it is a Frank Gehry structure. Next one is this Louis Vuitton, the famous fashion house. Louis Vuitton Museum, Foundation building at Paris. This is the model he showed. Now I said, what is this? All these sails are there, no sailboats. No, this is what is there. Obviously, the client has a lot of money to spend and doesn't mind anything, doing anything. Obviously, the prices are so high, their products. Obviously, they can afford that money. This is, when they construct it, this is how it looks like. And only the saving grace is they're all steel structures. So construction-wise and also analysis-wise, much better than, RCC structures, because that formwork itself would have been a problem. So how it looks like and how it was original and how it finally is such a, different feeling you have. And that is, I think, I come to the end. Yeah. So this is how I have learned. I have used finite elements, and in the process, every stage I have learned. Luckily for me, every problem was different from the other. So you had a scope to learn more, and if any problem was there that was not already solution available, knowledge was not, I had to explore, find out, and spend some time. And finally, it was a game. Finite element became like a game. You could play with it any way you like and apply it, so long as you don't make any gross mistakes, you'll always get something nice out of it. Thank you so much for listening. Now I will write any questions. Shekhar, you went out that time. I showed something. I said, you will be interested in that. I'll just... you were talking about the shear wall. I think that day also, yesterday night also, you were talking about the shear wall. How do you do this and all this? Then I said it can be done. But again, whether it is standard software you can do it or not, I am not sure for that. But if you have the liberty to modify it somehow, use something new in that, fit in some element, you can do it. See, each component, each wall of the shear wall, composite shear wall, that is not the, composite means is made of several walls, the individual walls, and becomes a one big shear wall of different form, different cross section. You can divide it using this element. This is, I used to use it for box girder bridges. And it works both for open section, thin-walled open section and thin-walled closed sections. So each wall you can use it. You require only one single node in the middle, top and bottom. And top, you can, all the nodes, you can use the diaphragm constraint, which is there in most of the things, so that that form is not allowed to go out of shape. If it is a channel section with 90-degree angles, it will remain 90-degree because your slab is there to confine into that form. It will not allow you to deflect individually each plate. So it's a diaphragm constraint as far as the plane is concerned. My own software. Yes, now. Yeah. Mm-hmm. Now, what do you mean by properties? You mean the Young's modulus?
Lot of things may change with the increasing temperature to very high degrees.
Mm.
For example, say a nuclear containment, temperature inside could be very high. Your thickness of wall is minimum 13 feet. I don't know, that is now...
No, you are going to a state of thermoplasticity. So...
I don't know because I'm not aware of anything, so I'm asking some maybe stupid question, but it is a question. Secondly, if you are designing a structure for earthquake analysis, in between some hinges and form, the stresses change. Will you be able to deal with that also?
First you have to find out the stresses.
Yeah, and then the condition changes, condition changes, somewhere hinges form, then the stretches are distributed differently. Whether all that is taken care of?
No. Single run will not taken care of. Will not take care of it. No single run will take care of it, everything together.
My question may be wrong itself, but...
No. What you are saying is, asking is correct. The point is, what I am saying that finite element will be able to take care of it, but not a single go.
No, this is the only question. I don't expect answer immediately.
First of all is to thank Professor Burgoyne. He had been an inspiration for me to analyze a lot of things, but I deviated from structures and did only projects directly. But what I want to actually emphasize is that it is so engrossing. Is there any reason why he was reluctant to leave, not join in the administration? He was wanting to continue in this because challenges here have been so high. You know, we all like to have challenges, and I think he had a challenge in numerical handling of all these structural problems. I think I appreciate that very much. And because I also get involved, not in this way, but in so many other ways, and most of us do that. We get engrossed in our work. Yeah.
See, I'll just one this thing. Finite element is only a way of learning how to do numerical analysis. You know, that way finite element principles I have used in surveying. You will know how, because somebody was from civil department was doing a, contouring, preparing a contour map of somewhere of Kalyan, something. There was a big drain going, long drain going. And he was having a hell of a time to calculate the cutting and filling whatever it is, all the terrains. Then he told me, you are using computer, can you do it? I said, you give me the contour grid and the contour values, and you also give the depth, width, and depth, and the cross-section of the channel that you want, and the levels. I looked at it, and then I divided into that grid into isoparametric elements, okay? That cutting thing, and calculated volume in no time. So my finite element thing helped me doing that quickly, because principle, after all, I'm calculating the volume only, and cutting, and I can, I'm not linear cutting, and it's taking undulations properly because of the isoparametric element formulation. Thanks.
We appreciate your lecture, sir, but I request the students and the faculty and all the civil engineers, those who have any questions, you can write to our email ID, issachq@hotmail.com. We'll try to compile that and send to Dr. Buragovind for his comments. Only one thing I just wanted to point out that since you talked about the commercial software packages like STAD and ETAP, to my understanding only they have, I think, the triangular elements and the quadrilateral elements, but they don't have the isoparametric elements as such, what my understanding is. And you have to just discretize those elements.
STAD is having that 8-noded element. STAD is having that 8-noded. I have used it.
Okay, no, it is having the solid element. Solid element is having 8-noded. 8s are, yeah. But still, now we are coming to the end of this session. Now we have to request our chief guest, Dr. Gupchup, also to just sum up and give his small remarks on this.
Friends, you have to admit that this talk by my good friend Dr. Buragovind was basically pointed to nuances. The word nuances are very important. Nuances of finite element method. I have known Dr. Buragovind for a very, very long time. And I've known that he's done a lot of work, practical work. And from the lecture you must have seen that this was not just a classroom talk. It was a talk full of practical examples which he has solved, and it gives us an inspiration. If you have problems, approach Dr. Buragovind. I'm sure he'll find some solution. Now, when Dr. Buragovind was in Mumbai IIT, I used to meet him, and then he was appointed the founder director of IIT Guwahati. He comes from Assam. And I think in a lighter vein, I asked him, I said, Dr. Buragovind, what is your address? He said, care of Indian Airlines. I have been traveling between Mumbai and Guwahati so many times. But then you know that at the end of the day, IIT Guwahati has come up thanks to his consistent, meticulous efforts. And now we have one more IIT, which is to be something to be proud of. I'm sure that all of us have enjoyed this highly educative and brilliant exposition, and we must thank Dr. Buragovind for it. We must also thank the Indian Society for Structural Engineers, Shekhar and Shantibai and Vadakar, everyone, for arranging this talk, which was a very illuminating one for all engineers and the students. So thank you very much, Buragovind. Hope to meet you again. Thank you.
Thank you, Professor Buragovind, for such a thought-provoking and deeply insightful session. and thank you, Dr. Gupchup, for sharing your reflections and words of wisdom with us. We also remind the audience that this talk is being recorded and it is available online on the official VJTI YouTube channel. Now, to formally conclude the session, I may now invite Engineer Ranganath Satham, Honorable Secretary, to deliver his vote of thanks.
बंद कर देना. Very good evening to one and all. It's my distinct pleasure to propose a vote of thanks on this memorable occasion on behalf of an ISSC as well as on VCTI. I would like to express our sincere and heartfelt gratitude to every one of you for gracing us with your presence and contributing to the success of this event. First and foremost, I extend profound thanks to our esteemed chief guest, Dr. V.N. Gupchup sir, ex-principal of VJTI. So thank you for honoring us with your presence. Special very thanks to keynote speaker, Dr. Professor D.N. Buragohan, for your presentation, which was incredibly enlightening us and given us a detail to ponder on that. The depth of your knowledge and ability to present is also compelling, is a true comparable. Thank you for sharing your valuable experience with us. We are deeply grateful to Professor Sangale, the former HOD of Structural Department VJTI, for all welcome for such an event, wonderful tone for the evening. We also thank Dr. Professor Deshmukh, HOD of Structural Department VJTI, for graciously making the VJTI Auditorium and its resource space available for the event. We are grateful to Professor Tarun Khan sir, Dr. Abhay Bambole sir, the Dean of Infrastructure VJTI, Senior Consultant Dr. Kilkar, Shantilal Jain sir, Past President of an ISSC, all senior professors, professionals and consultants. I would also like to thank Mr. Shekhar Ghate for his fluent introduction of our speakers and his tireless effort in organizing today's event. Our gratitude also goes to President ISSC Hemant Vadalkar for insightful address on ISSC's purpose and functions. Vote of thanks never be complete without acknowledging our audience. I must thank you for being so engaged and participative. Your thoughtful questions added another dimensions to the discussion. Finally, I would like to thank a massive thanks to the entire organizing team, VJTI staff, for their tireless efforts and meticulous planning behind the scenes have made this event great success. Also, thank to Dr. Patel, the compare for the today's event. I was once again appeal to the all participants who are not yet member to consider the joining of an ISSC and becoming part of our growing community. The forms are there on the outside on the desk, so you can become a member of that. And before we conclude, I request all to kindly stand for the national anthem.
With that, we bring this wonderful evening to a close. We now invite you all to join us for the dinner at the canteen section. Thank you very much.